In this lecture, we will take a closer look at the maximum modulus principle. The Phragmen Lindelof method is, in some sense, a generalization of the maximum modulus principle to the unbounded domains in the complex plane. Let's look at the exact variant of the maximum modulus principle. We will be interested in this lecture, and how we'll discuss how the Phragmen Lindelof method generalizes that particular statement. We have already seen a couple of variants of the maximum modulus principle. Nevertheless, so the lecture is on the Phragmen Lindelof method. This is more of a method. We will describe more what this method is over the course of this lecture. So let omega in this case be a bounded open connected set in C, and f be a function defined on omega bar into C, be continuous on omega bar and holomorphic on omega. So this is a function which is holomorphic. It's a function which is holomorphic on omega, but we have slightly more extra conditions on f. F is also defined on omega bar, and on omega bar the function is continuous. Of course, holomorphicity on omega certainly implies continuity of omega, but we didn't know anything about how the function f behaved on the boundary of omega, which is also now a part of omega bar. We are demanding that f extends continuously up to the boundary. That is the condition we have put forward. Now, if f is non-constant, suppose f is not a constant function, then f being a holomorphic function on omega, and the open mapping theorem tells us that by the open mapping theorem, there does not exist z0 in omega such that f attains, maybe let's call it z1 in omega, such that f attains a local maximum at z1. This is something which we had discussed earlier in one of the problem sessions. Because it's an open mapping, there will be a ball around z1 which is contained in f of omega, and therefore you will be able to get hold of some z2 which has absolute value greater than f of z2 will have absolute value greater than f of z1, absolute value of f of z1, and therefore it cannot have a local maximum. However, because f is continuous on omega bar, since f is continuous on omega bar and omega is bounded, I have put that assumption here. As you can see, omega bar is going to be a closed bounded set, which by the Hein-Borel theorem is compact, and since omega bar is compact and f is continuous on omega, there exists z0 in omega bar such that the maximum or the supremum is attained at the point z0. Because it's compact, we can say this, right? This is the supremum of z in omega bar, absolute value of f of z. By the previous discussion, we just noted that our point z0 cannot be in the domain omega, and hence the point z0 is in the boundary of omega, and that's the exact statement of the maximum modulus principle we are going to discuss in this particular lecture. So hence, what do we conclude? Supremum of absolute value of f of z for z in the boundary of omega, z in omega, this is equal to the supremum of absolute value of f of z for z in the boundary of omega. And if z0, if the supremum is attained at some point, interior point, if the supremum is attained at an interior point, that's possible only if our function f is constant. Then f is constant. Notice how crucially we used the fact here that there exists a point z0 such that the absolute value is attained. we have used the fact that omega is bounded very crucially to state this variant of the maximum modulus principle. And the problem is that when we ask a similar question to question on unbounded domains, we do not have such an answer. In fact, this exact statement when considered in unbounded domains is going to be false. Let me give you an example to illustrate that this particular statement will not go through for unbounded domains. Consider omega, which is the horizontal strip. It is the set of all z in C such that minus of pi by 2 is less than the imaginary part of z, which is less than pi by 2. So if I am to draw it on the complex plane, let these be the axis. Let me use the red line to capture plus pi by 2 and minus pi by 2. Suppose we have the strip, so the region shaded in green is what we are considering. The imaginary part is between minus pi by 2 here and plus pi by 2 here. So in this region, consider the following function. Let f of z be defined to be e to the power z. It's not looking good, so let me write it as x of z. What can we say about the absolute value of f of z on the boundary? On boundary of omega, z is going to be equal to x plus or minus I pi by 2. Right? Every point on the boundary will be some x plus or minus I times pi by 2. X of x plus or minus I pi by 2, this is going to be equal to e to the power x, and times e to the power I pi by 2 is just going to be equal to cos of pi by 2 plus I sin pi by 2. So this is just going to be equal to plus or minus I times e to the power x. So if you look at f of x plus or minus I pi by 2, this is just going to be, and look at the absolute value, this is the absolute value of the x of plus or minus I times e to the power x, which is going to be a point on the unit circle. This is just going to be equal to 1. So the absolute value of f on the boundary is equal to 1. Oh, before that, notice that our function f is the composition of the exponential with itself, and therefore it's going to be an entire function. In fact, it's certainly holomorphic on the strip, green strip that we have defined, and we noted that on the boundary this is equal to 1, and if you look at the limit as x goes to infinity of f of x, this is blowing up, this is going to blow up to infinity. So clearly our maximum modulus principle fails in this particular setup. So what went wrong? Clearly the fact that omega is bounded was playing a crucial role. We dropped the condition that omega is bounded and we ended up with this kind of a situation. So we'll ask the next question, as mathematicians generally do. What is the next best thing that can be done? And that is where the Phragmen Lindelof method comes into our picture. But before I get into the method and describe a couple of application of the method, let me give you an analogy. When we looked at the Liouville's theorem, what did Liouville's theorem tell us? Liouville's theorem told us that bounded entire functions are necessarily constant. But then if I impose the following condition, suppose f is an entire function, it's holomorphic on the entire complex plane, and instead of bounded at every point, let me just assume that it is having a growth, not just m, it's having a plus mod z to the power 1 by 2. The 1 by 2 is could be replaced by any number less than 1, it would still work, but let me just stick to 1 by 2 right now. My claim is that all bounded functions with this growth condition is also going to be constant. So the proof is actually very similar to how we proved Liouville's theorem. So for or on the disk of radius r around 0, what do we have? We have absolute value of fn of 0 by the Cauchy's estimates. This is going to be less than or equal to n factorial into the absolute value of f on the boundary, which is less than or equal to m plus mod z to the power 1 by 2, and that is exactly equal to m plus capital R to the power 1 by 2, and this is divided by R to the power n. This is precisely our derivative of f, nth derivative of f evaluated at 0, and as R goes to infinity, this is an entire function, so we can let R go to infinity. This is still true for every R, and we get to conclude that fn of 0 is equal to 0 for all n greater than or equal to 1. But what does that mean? That means that if f of z has a power series expansion summation a n z to the power n around 0, around the origin, then a n is going to be equal to 0 for all n greater than or equal to 1, which means that f of z is a0, which is a constant. So even with a weaker growth condition like this, we will be able to conclude the same result as Liouville's theorem. Let's do something similar here. We will impose some growth conditions on our function f, and then we will ask whether we can conclude something similar to the maximum modulus principle. And that is where our Phragmen Lindelof method comes into the picture. So let me just state the first theorem. We will prove it for very specific strips. We will prove generalization of the maximum modulus principle for strips, for very specific strips. Let's look into the statement, and then we will discuss further. Let f, or rather let omega, be the set of all z in omega such that a is less than the real part of x is less than b. So the strip we are considering is the following: x is going to be having some bounds like this. So this is going to be, why should we draw it like this? Let's not give the idea that it has to be on both sides of the y-axis. So let me just draw the a's and b's like this. It could be negative as well. So let a be here and b be here, and we are considering this particular strip. So let's take one such unbounded domain, and let f be a function which is defined on omega bar, where f is continuous on omega and omega bar and holomorphic on omega, just like in the previous case. Suppose instead of putting growth conditions immediately, let's look at a function which is bounded. Suppose, so yeah, one shouldn't wonder that if we already start off with a bounded function, then why are we doing this? That's not the point. The point is that this b is not something which is given to us. B could be very, 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 very large. It might have nothing to do with the boundary as of now. Suppose we start with a function which satisfies the condition that absolute value of f of z is less than b, and let m of x be equal to the supremum of the absolute value of f of x plus iy, where the x is fixed and y is being varied. If you look at what is it in the geometric sense, we take this purple line, so we fix a point x here, and you look at this particular purple line and look at the supremum of absolute value of f of z on this purple line. That's precisely what is being captured by m of x. The conclusion is that m of x to the power b minus a, this is less than or equal to m of a to the power b minus x into m of b to the power x minus a. So my first observation here would be to point out to you that this actually tells us that the absolute value of f of z is bounded by the supremum on the boundary. Let's see why that is coming out to be the case. For So this is the statement of the theorem that we just discussed. For z in omega, if you look at the absolute value of f of z, that's going to be less than or equal to m of x, where our z is x plus iy. If you look at m of x, because what was m of x? M of x was the supremum of the absolute value of f of x plus iy, where x is fixed and y is varying. So in particular, this absolute value of f of z is less than or equal to m of x, and this is going to be less than or equal to the max of either m of a or m of b. Because if say m of a was greater than m of b, this thing on the right would then be less than or equal to m of a to the power b minus x plus x minus a, which will be b minus a. So then it would become less than or equal to m of a. And if it was m of b which was greater than m of a, then this would again be less than or equal to m of b to the power b minus x plus x minus a, which is b minus a. So m of x to the power b minus a would be less than or equal to m of x to the power maximum of one of the two, m of a to the power b minus a or m of b to the power b minus a, and hence, because we started off with positive numbers, this is going to manifest in saying that m of x is less than or equal to m of a or m of b, whichever was bigger. So we certainly have this, and this is exactly equal to the supremum of the absolute value of f of z for z in the boundary of omega. So this is what the maximum modulus principle statements generally tell us. So that's what we will be able to conclude. So it doesn't matter what this b is. The moment we know that the function is bounded, then we will be able to conclude that absolute value of f of z is less than or equal to the absolute value on the boundary. All right, let's give a proof of this statement. Let's just go back to the statement and see what it did. The theorem states that if we have a function f which is holomorphic on the green shaded region and such that it is continuous on the closure, then m of x, which is defined as the supremum on the say purple line, where the purple line hits the real axis at the point x, that supremum is going to satisfy this particular inequality. Let's give a proof of this statement. We will assume, let's assume that m of a and m of b both are equal to 1. We will see later that this condition suffices and that the general case follows if we do that. Let's first prove this statement for m of a and m of b. Now is where the Phragmen Lindelof method comes into the picture. We are going to introduce an auxiliary function, define h epsilon of z, the auxiliary function that we will be dealing with, as 1 by 1 plus epsilon times z minus a. Let's look at this function for a few minutes. The first observation would be that 1 plus epsilon times z minus a, if you consider the real part of this is exactly equal to 1 plus epsilon times x minus a. For any epsilon positive, we have that this is equal to 1 plus x minus a, epsilon times x minus a, which is going to be greater than 1 because x is between a and b, and hence x minus a is positive, so this is going to be greater than 1. But then if you look at the absolute value of notice that this is a positive number, so the absolute value is going to be the same, and this is going to be the absolute value of 1 plus epsilon times z minus a, which will be bounded by the number on the right, bounded below by the number on the right. This is just going to follow from the usual fact that mod z is going to be greater than the absolute value of the real part of a, real part of z rather. And therefore, this helps us in concluding that h epsilon of z is less than 1 by 1 plus epsilon times z minus a, which is less than 1. And this is true for all z in omega bar, in fact. right? So what happens in the case of, so maybe I should put greater than or equal to 1, because when z is on the boundary, it can happen that x is equal to a, and in that case it will be equal to 1. So this will be less than or equal to 1. That's precisely what we get to conclude. Now what do we know about our function f on the boundary? Notice that m of a is equal to 1, and this is the same as m of b. So for all z in the boundary of omega, we have f of z is less than or equal to 1, right? Because m of a is the supremum of the absolute value of f of a plus I y, where y is ranging from minus infinity to infinity. So in particular, we have mod f of z is less than or equal to 1 on the boundary, and that gives us that absolute value of f times h epsilon is less than or equal to 1 on the boundary of omega. So let's just go up and look at what we did. We ensured that on these two red lines, which uh, are situated at x is equal to a and x is equal to b, our function h epsilon times f is bounded by 1 above. So if z is equal to x plus iy, let's now focus on the imaginary part. What can we say about the imaginary part of 1 plus epsilon times z minus a? This is going to be equal to the epsilon times the imaginary part of z. A and 1 both are real numbers, they will not contribute, and hence we get it here. So the absolute value of 1 plus epsilon times z minus a, if you look at this number, that's going to be greater than the absolute value of the imaginary part, which is exactly equal to epsilon times mod y. So in particular, h epsilon of z is also bounded by 1 by epsilon times y, and therefore f times h epsilon is bounded by b, because f is bounded above by b. Did I put the bound as b or as m? I put it as p. So let's stick to it, and this is going to be less than b by epsilon times mod y. Now let's look at the strip, which is consider mod y, which is greater than epsilon by b, then 1 by, or maybe b by epsilon. And then what do we have? This means that b by epsilon times mod y is going to be less than 1, right? So on this set of all z such that mod y is greater than b greater than or equal to b by epsilon, this is going to be less than or equal to 1, which tells us that absolute value of f h epsilon of z, this is going to be less than or equal to 1 if the imaginary part, absolute value of the imaginary part of z is greater than or equal to b by epsilon. So let me just go, or maybe I'll draw the picture once again. We are in the setup like this here, and our red lines were capturing the a's and b's, and what it is telling us is that if you look at the pink, which is capturing the imaginary part being, maybe not pink, the green, let me take the green to capture imaginary part of z above uh, b minus epsilon, that's going to be this region which is now being shaded. So what we have just established is that in this shaded region, all the way going up to infinity in both the directions, our function f h epsilon is less than or equal to 1. Now by picking green, by picking the orange and capturing the boundary, this boundary is the boundary of a rectangle. Now let R be the rectangle with the boundary given by the orange lines. Let me not write down explicitly what the boundary is, I'll leave it to you. In fact, I'll give you a glimpse of what the boundary can be described as. It will be x is equal to a, y between minus of b by epsilon to b by epsilon, Similarly, the next one will be y is equal to minus b by epsilon. X is between a and b. The third line will be x is equal to b. Y is going to be between minus b by epsilon and b by epsilon. Fourth line will be y is equal to b by epsilon, and x is between b and a and b rather. So those are the four sides of the rectangle. Let's now consider the function f restricted to the closed rectangle, to a neighborhood of the closed rectangle R, and apply the maximum modulus principle. Observe that absolute value of f of z is less than or equal to 1 on the boundary of R. That is what we were ensuring all the way here, right? So here we ensured that it is less than or equal to 1 on the horizontal lines, and earlier we did establish already that the entire vertical lines which form the boundary, this is less than or equal to 1. So in particular, in the boundary, on the boundary of the rectangle, absolute value of f of z is less than or equal to 1, and by the usual maximum modulus principle, absolute value of f of z is less than or equal to 1 on R. And we already have that in the shaded region, we already have that absolute value is less than or equal to 1. Absolute value of f times h epsilon. So let me not make the fundamental mistake here. This is what we'll get to conclude. So we get to conclude that f times h epsilon of z is less than or equal to 1 on R. And by combining this with the observation star here, star gives absolute value of fh epsilon of z is less than or equal to 1 on omega bar rather. But now if you notice, for each z in omega, what was h epsilon? H epsilon of z, this is equal to 1 by 1 plus epsilon times z minus a. And as epsilon goes to 0, h epsilon goes to 1, and as epsilon goes to hence 0, we have f times h epsilon of z converges to f of z. For every z in omega and for every epsilon positive, we have this. This tells us that absolute value of f of z is less than or equal to 1. And that is precisely what we were trying to conclude, because now we have m of x is going to be less than or equal to 1 to the power x minus a times 1 to the power, which is 1. Therefore, we have established this result in the case when we have assumed that m of a and m of b both are equal to 1. Let's now prove the more general case. Now we are not assuming that the numbers m of a and m of b are 1. We know that m of a and m of b are some real numbers, positive real numbers. And then let's try to prove the result in the more general case. In order to do that, let's define our g of z to be equal to log, or maybe exponential of b minus z by b minus a times log m of a. This is basically the real logarithm times the exponential of z minus a by b minus a into log m of b. So if you notice, exponential of b minus z by b minus a into log m of a is a composition of entire functions. B minus z by b minus a is a entire. Notice that the thing inside the green actually is a real number. So log m of a whole divided by b minus a is actually a real number, and a real number times b minus z is an entire function, and exponential of an entire function is again going to be an entire function. So this thing which I just underlined in green is an entire function. This is also an entire function, and therefore g of z is a function which is an entire function. That's the first observation we would like to make. Let's now see what happens when we look at g on the boundary of omega. So if you look at the absolute value of g of a plus iy, let's see what happens to that. Then this is going to be equal to the b minus z will contribute b minus a, and the other absolute value will be, okay, let me just write it down. This is going to be exponential of log m of a plus I times something, which I will not write because the absolute value will not contribute. This will not contribute to the absolute value. Similarly, this is going to be exponential of z minus a. In this case, the real part will be 0 and there will be I times something, which again I will not write down because the absolute value will not contribute. Here this is going to be equal to 1. The thing which I have just marked will also contribute to be 1, and this is going to be equal to the exponential of log m of a, and that's going to be equal to m of a. And very similarly, we can conclude that the absolute value of g of b plus iy, this is going to be equal to m of b. So g is a function which on the boundary takes the value m of a, and on the boundary x is equal to a, it takes the value m of a, and on the boundary x is equal to b, it takes the value m of b. Also notice that it's an exercise to notice that g is, because it's the exponential of the function f, which is given by b minus z by b minus a into log m of a, it's not going to have zeros. So g does not have zeros, and moreover 1 by g is bounded. That is the exercise for you. Sit down and check that 1 by g indeed is a bounded function on omega bar. That's not going to be difficult because, as you can see, the real part is contributing to the absolute value, and that is bounded. So we will certainly, in fact, we will be able to show that this is less than or equal to 1. Anyway, once you have both, consider the function f by g, and f by g will satisfy the exact same things as earlier, and therefore we will be able to conclude that the absolute value of f of z by g of z is less than or equal to 1, and hence we will be able to conclude that absolute value of f of z is less than or equal to g of z, and from there we will be able to get hold of the result. So let me just leave that as an exercise, and we have absolute value of f of z by g of z is less than or equal to 1 for all z in omega bar. Conclude the result in the general case. So what did we do in this entire result, in this entire theorem? What we did was we somehow introduced an auxiliary function here, h epsilon, and using this h epsilon, we reduced the problem partly to a problem of the maximum modulus principle being applied on some bounded function, a bounded domain. And that's precisely what is referred to as the Phragmen Lindelof method. Let's look at one more example of the Phragmen Lindelof method on another unbounded domain, which now is going to be a horizontal strip rather than a vertical strip. So let me just state the theorem down for you. Now our omega is going to be the set of all z in omega such that the imaginary part of z is between minus pi by 2 and pi by 2. So this is the domain we considered earlier. In this case, it's quite straightforward. This is going to be minus pi by 2, and say this is going to be pi by 2, or the converse rather. And you look at the shaded region, which is now given by green, and we already saw that e to the power z is a function which gives you a counterexample to the classical statement of maximum modulus principle, which is given for bounded domain. So we'll now see what is the next best thing that can be done to still conclude something about the maximum modulus principle here. And going by the analogy that we gave earlier with Liouville's theorem, let's just consider a function which is defined on omega bar, which is continuous on omega bar and holomorphic on omega. Suppose absolute value of f of z is less than or equal to 1 on the boundary of omega. Absolute value of f of z is less than or equal to the exp of some capital A times the exp of alpha times the absolute value of x, where there are quite a few things to be explained, where what is x? Z is equal to x plus iy. A is some finite number and some real number, and alpha is less than 1. So these are the conditions of the growth of our function f that is being imposed. Then we can conclude that f of z is less than or equal to n on omega. So notice that we already have the bound of f as being less than or equal to 1 on omega. Notice again that the function e to the power z does not satisfy. For alpha equal to 1, this is not true. That's precisely what the counter example earlier told us. The moment we have such a growth condition where alpha is less than 1, we will be able to conclude that our function f is bounded by 1. The strategy of the proof is going to be the same. We will define an auxiliary function and we will use that to reduce it to proving the theorem by using the maximum modulus principle on some finite domain, some bounded domain. But before that, let's pick a beta positive such that alpha is less than beta less than 1. Let's pick one such beta, and for any epsilon positive, let's define an auxiliary function h epsilon of z, define h epsilon of z to be equal to the exp of minus of epsilon times e to the power beta z plus e to the power minus of beta z. Let's now try to conclude that the absolute value of h epsilon is less than or equal to 1 on the entire domain omega. So before we do that, notice that if you want to consider the absolute value here, that's going to be the absolute value of the exponential of whatever is there inside the bracket. The first observation would be that whatever is there inside the bracket, only the real part of that contributes to the absolute value here. So let's focus on what is the real part of minus of epsilon times beta z e to the power beta z plus e to the power minus beta z. Let's focus on this and notice that this is just going to be equal to minus of epsilon times e to the power beta x plus e to the power minus beta x times cos beta y. This is precisely what will be inside the real part of minus of epsilon. Why is that the case? Because this is going to be equal to e to the power beta x plus I beta y. So the I beta y will have a cos beta y, and here there will be e to the power minus beta x minus I beta y, and again real part will have cos of minus beta y, which is the same as cos beta y. That's how it came out here. So this is going to be exactly equal to whatever is written here on the right. And notice that cos beta y is going to be between minus pi by 2 and pi by 2, and therefore this is going to be less than cos of beta times pi by 2. Beta is less than 1, strictly less than 1. Remember, our choice of beta was between alpha and 1 for some beta positive. So this is going to be strictly less than pi by 2, and therefore this is not going to be 0. So cos beta y will be a number which is strictly less than some, say, delta. Also, because y is between minus pi by 2 and pi by 2 and beta is positive, cos beta y will be a positive number. So we are in good shape. So let's now put that in here. So what do we have? Hence, absolute value of h epsilon of z, this is going to be equal to the x of minus epsilon times e to the power beta x plus e to the power minus beta x times cos beta y, which is less than or equal to, because cos beta y is less than or equal to this delta that we wrote, this is going to be equal to x of minus epsilon delta e to the power beta x plus e to the power minus beta x. Now, exponential of beta times x, beta and x both are real numbers. Exponential of minus of beta x, again both are real numbers. This is always going to be greater than or equal to 0. In fact, it will be greater than 0. Therefore, minus epsilon into delta into whatever is written inside the bracket, that's going to be a negative number, and therefore this is going to be less than 1. And hence this function is less than 1. And that is precisely what we were trying to conclude. H epsilon, notice, is less than 1 on on the entire domain omega bar. So this is true on omega bar. The choice of H epsilon might seem a bit strange, but remember that we have a growth condition on our f of z here as well. So let's now look at what happens to f times h epsilon. Now let us consider the function f times h epsilon. Consider f times h epsilon. We already know that f is bounded by 1 on the boundary, and therefore absolute value of f h epsilon of z is less than or equal to 1 on the boundary of omega. So in this image, on the red lines, we have f times h epsilon is already less than or equal to 1. We would like to now study what happens at other points. Let's see what happens at other points. We know that f has a growth condition. So in particular, we have f h epsilon of z is going to be less than or equal to the absolute value of f of z, which we have bounded by this particular quantity x of a into x of alpha mod x. So this is x of a into e to the power alpha times mod x. And what about h epsilon? H epsilon is exactly equal to x of, it's bounded by minus epsilon delta. Let me just put the bound that we already obtained. This is the bound. Minus epsilon delta times e to the power beta x plus e to the power minus beta x. This is precisely the bound that we have when we look at arbitrary points of omega. So this is true for z in omega. The exponent here that is being underlined has the nice property that as x goes to infinity or as x goes to minus infinity, whatever is underlined is going to converge to minus infinity. So that's going to be some real analysis for you, which I will write as an exercise. Check that a e to the power alpha times mod x minus epsilon into delta times e to the power beta x plus e to the power minus beta x. This converges to minus infinity as x goes to infinity or as x goes to minus infinity. When x goes to infinity, the e to the power beta x term kicks in, and as x goes to minus infinity, e to the power minus beta x term kicks in. The minus epsilon times delta will ensure that that goes to minus infinity. Remember that beta is greater than alpha, so that's going to contribute to concluding this particular exercise. But that's good, because the moment the exponent is going to minus infinity as x goes to infinity, what do we have? This implies that the absolute value of fh epsilon of z, this is going to be less than 1 for mod x greater than x naught, because as x goes to infinity, the exponent is going to minus infinity, and therefore the absolute value of fh epsilon of z is going to come down to 0. So at some point of time, it will be less than 1, and let that be captured by mod x greater than x naught, greater than or equal to x naught. So notice what has happened here. Maybe I should draw the picture again. The picture is now going to be exactly like this. There is plus pi by 2, there is minus pi by 2, and the dark green line is going to be mod x greater than or equal to x naught. So this is minus x naught, this is x naught. So in this region, what we have just established is that in the region which I am now shading by light green, so here it will be to the right, this region, we have just established that our function h epsilon times f is having absolute value less than or equal to 1. Now, like the previous problem, by applying maximum modulus to f h epsilon on R, where R is again given by the orange rectangle here, where R is the rectangle with sides x is equal to x naught, x is equal to minus x naught, y is equal to plus or minus pi by 2. If you look at this particular rectangle, on boundary of this rectangle, absolute value of f h epsilon of z, this is less than or equal to 1. And by the maximum modulus on R, we have absolute value of f h epsilon of z. This is the maximum modulus principle. This is less than or equal to 1 on R. So not just the boundary of R, on R as well we have this is less than or equal to 1. And hence, absolute value of f h epsilon of z is less than or equal to 1 on omega bar. So using this auxiliary function, what we have concluded is that the absolute value of f h epsilon is going to be less than or equal to 1 on the entire boundary, on the entire domain omega bar. But this is true for every epsilon. Notice that h epsilon of z, what was h epsilon of z? Let me go up and remind you what h epsilon of z was. H epsilon of z was e to the power minus epsilon of e to the power beta z plus e to the power minus beta z. And as epsilon goes to 0, for every z, this converges to 1. H epsilon converges to 1 for all as epsilon goes to 0 for all z in omega bar. And that tells us that absolute value of f of z, this is also less than or equal to 1 on omega bar, just like how we had expected to conclude. So with this we conclude the theorem. So the point here is to observe that in both these cases, an auxiliary function was introduced to get hold of the maximum modulus principle, which can be now applied to the function which has a good growth condition to conclude a similar result as to maximum modulus principle.